Okay, let's get going. Today we are going to continue to talk about the STAN language. So I will continue to tell you that Columbia gets a lot of grants for STAN. I work for Columbia. I also work for STAN Group. It's conflict of interest that has to be disclosed in presentations such as this. So we're going to be doing a bunch of examples, writing STAN programs, getting more practice, how to call them, etc. That's something that you need to practice on. The STAN language takes a little bit of time to pick up. It's a bit more formal than the R language in some respects, but it's not a very difficult language. It basically just has integers and real numbers and containers thereof. And it already has a lot of functions that you can use to specify posterior kernel and log units, which is what you need to do in order to draw from a posterior distribution using STAN. But it doesn't do you a whole lot of good to spend the past 2 or 3 months learning how to do Bayesian analysis, being able to draw from any posterior distribution that's differentiable with respect to all of its unknowns, if you can't write down a posterior kernel that is differentiable with respect to all its unknowns. And that has, very little really to do with the STAN language or Bayesian analysis. It's just an aspect of sort of translating your model mathematically or conceptually into code. If you were to do, maximum likelihood estimation, which you can actually do in STAN, but I'm not going to tell you how, it would involve all the same steps except for the step where you specify what the prior distribution of the parameters is. And then you would, execute the thing using an optimization algorithm rather than MCMC algorithm. But writing down like 95% of the model would be exactly the same. And so that's really something that we need to learn how to do. So if we're calling this from R, we load up the RSTAN package. If I switch over to my RStudio window, you notice when it does that, it says a lot of stuff that's not too relevant. It also says for execution on a local multi-core CPU, which would basically be your laptop, with excess memory. We recommend calling, we kind of recommend calling that always RSTAN underscore options auto underscore write equal true. That will write a compiled version of your STAN model to the same directory where your STAN program is saved. If you load that up in a subsequent R session on that computer, you won't have to recompile it again, which can take like 30 seconds, 60 seconds, something like that. So that is pretty useful. You might think that you can compile a STAN model on your computer and like post it to Instagram or something like that and get all your friends to download it and they can use it. That is false. The instructions in that binary file are specific to your computer and it most likely will not work on anyone else's computer. Maybe if you do like identical version of operating system, identical version of compiler, something like that, it might work, but don't hold your breath. Perhaps more importantly, it suggests in the case where you have multiple cores and excess RAM to call options parentheses mc.cores equal parallel : detect cores parentheses. That will use as many cores, that will detect how many cores you have available on your computer and use up to that many cores, 1 core per chain when estimating this. So you can do like 4 or 8 or whatever chains simultaneously. And that tends to be faster as long as you have enough RAM than doing the chains serially or consecutively. Adam, you had a question?
Yeah. What does excess RAM mean?
Well, you never know until you run out. But one thing that can make Stan go extremely slow is if you run out of memory and have to use your swap drive or partition to like write stuff to the disk that should be in memory, and then it uses the other stuff, and then it needs the stuff off the disk. So if you're using swap partition, or what Windows at least used to call virtual memory, which is basically hard disk, to store stuff, then Stan is just going to be extremely slow because all the reading and writing from the disk takes longer than like solving Hamiltonian equations. Now, doing this in parallel eats more RAM. One, you have like 4 or 8 things going simultaneously. It has to make that many copies of the data. So if you have like a big data set and you copy it 4 times to do 4 chains in parallel, that's going to take up 4 times as much RAM. Yeah, whatever you have to do to keep it in RAM and not touch the swap, inclusive of buy a better computer. Yes.
Do you have to run that code, that course code, only once at the beginning, or do you have to run
Once per our session, yeah. Other questions? No, okay. Switching back to this. So there is a data set called trees in R that has 3 variables about trees that were cut down for timber. The volume, the height, and the girth, which I think is a synonym for circumference, or maybe radius, I don't know. Geometrically speaking, there is a relationship between the volume of a cylinder and its radius and height. Trees are approximately a cylinder. However, the relationship between the volume of a cylinder is a multiplicative formula. It's the area of the base multiplied by the height. So if we wanted to do linear regression, it would behoove us to do that in the logarithms of these variables, where we would expect the multiplicative relationship to become additive in the logarithms of these positive numbers. So in order to prepare a named list of things in R, where the names should correspond to the same names that are declared in the data block of your Stan program, we can do something like this. Use the width function to evaluate the following expression, where it's going to look inside the trees data set for these. We'll create a variable called y, which is the log of volume, and we'll create a matrix X, which has the logarithm of the other 2 variables. We'll make that as a matrix. And then after that, we'll specify n and k, the number of observations, in this case 31, and the number of predictors in X, which in this case is 2. So now all we have to do is write a Stan program that implements a linear regression model and takes as the names of the things in its data block the same names that are in this named list that we're going to pass to Stan when we call the Stan function in the RStan package. Everybody understand what we're attempting to do here? Okay. So all we have to do at this point is write a Stan program called linear_regression.stan and save it to our working directory, or the same directory where we have our markdown file or something like that. Okay, so to do that, We create a text file. We save it as linear regression.stan. RStudio then recognizes this as a Stan program, and we can proceed to write it down. So how would we do that? The blocks. So we're going to need data. We're going to need parameters. We're going to need a model. That's kind of the minimum number. We might also need transform data, transform parameters, generated quantities. But we're going to need at least those three. And in the model block, we're going to have to build up an expression for the kernel of the posterior distribution we want to draw from in log units. So what will we do? X.
And the regression model, y, the log of y.
Okay, so we're already going to pass in the outcome in log.
Yeah, so it's y.
Right. Okay. So you're saying we should do the likelihood first. All right. So that would be in the model block. How would we write the log likelihood for these data under a linear regression model? Target plus equals. Target plus equals what? Normal. LPDF. So we want to use the logarithm of the PDF of the normal distribution for our likelihood. And if you pass one of these underscore LPDF functions in Stan, a vector or a one-dimensional array, it will add up the log likelihood contributions for the individual observations, sum them all up, return a scalar for the log likelihood of the data as a whole. So what do we need to put inside normal underscore LPDF to implement the log likelihood for a linear regression model? Why? What comes after y? Vertical bar, indicating what we are conditioning on. So what is the conditional mean function for a linear regression model? Conditional on x. Yeah, we've put that into x. What do we do with x to give us a conditional regression relationship between y and x? There's a what? There's a beta. What do we do with that beta? Okay, we could do a QR reparameterization. That'd be a little bit advanced given our progress so far today, but we could do that. Beta times X, except the other way around. X times beta is a more typical way to do that. But that presumes that the first column of X has a vector of ones, which it does not in this case, meaning we need to separately add an intercept term in the usual case that we have a non-zero intercept in our model. In the case of this, we expect the intercept to be pretty close to the negative logarithm of 2 pi because the area of the base involves pi. Anyway, so yes, we would have an intercept in almost all cases where we have a linear regression model. Okay, so that is the log likelihood for alpha and beta. What else do we need to specify a normal likelihood? Sigma. What else do we need to specify a normal likelihood? Okay, we need the prior for the kernel. What else do we need for the likelihood? What? Well, mu is implicitly here equal to alpha plus x times beta. Theta? Oh yeah, we're gonna need data. Yeah, definitely. But we already sort of did that in R. All we have to do is the corresponding thing in Stan. But it couldn't hurt to do that next. So what are the names of the things we're passing from R to Stan that we are going to need in the data block of our Stan program?
Y and X.
Y and X. Okay. What is X? Contains real numbers. Matrix. And when declaring a matrix, what do we need to tell Stan? Huh?
Size of the matrix.
The rows and columns of the matrix, which are what? N and K. Meaning, we're going to have to define what N and K are prior to declaring X. So what is N? Did I catch an int? Yes. Specifically, an int that is greater than or equal to 0. And what is K? Int. Specifically a non-negative integer. One thing that you will see often, which is a sure sign of an incompetent Stan programmer, is to not declare K and instead put something like n by 2 for x, because in this particular case, x has 2 columns, and you could get this to work for this particular data set. However, it would not work for any linear regression model that did not involve 2 predictors. You would have to change the 2 to whatever is the number of columns of x every time you wanted to use this program. Therefore, it is much better to instead specify x as a n by k matrix, passing in both n and k, and then the program will work for any non-negative integers n and k. That principle holds more generally, and that if you're going to take the time to write a STAN program, you should write it in such a way that it is more general than what you need for the specific problem that you're trying to use it for, so that you can reuse it, hopefully with minimal, ideally 0 changes, the next time you need to estimate a model like this. So, you know, that's why we declare sort of a generic predictor matrix X instead of having like 2 vectors, one like log width and the other log height. That only works for trees. We want to write a regression program that would work for anything. Okay, what's Y? It's a what? Could be a vector. And if it were a vector, what would we need to specify? The number of rows, which is n, correct? We could also declare this as a real array of length n. Since we're not using Y for linear algebra purposes, it's perhaps a little bit clearer and safer to declare it as a real array rather than a vector. But if we needed to use Y for linear algebra purposes, then it would have to be a vector properly. Okay, we have the data. We have the likelihood of the data. What do we need now? Priors on what? Or in general, parameters that we declare in the parameters block, which we have not done yet. So let's do that now. What is the nature of alpha? It is a real number. And what is the nature of beta? It's a what?
Real array.
Could be a real array, but given that we want to use it in a linear algebra context later in the model when we post multiply the matrix X by the vector. So when declaring a vector, what do we need to specify? The number of rows, which is K, making it conformable for multiplication with the n by k matrix X. Okay, what else do we need to specify in the parameters block of a STAN program for linear regression? Sigma. What is the nature of sigma? It's a what? It's a non-negative real number. How would we indicate that in a Stan declaration? Lower equals 0, angle bracket, sigma. All right, now we have parameters. One step to go to define a posterior kernel in log units. And what is that remaining step? Priors on alpha, beta, and sigma. So let's start with beta. What do you believe about these two coefficients in this context? Normal. Okay. And if they are normal, what are their means, prior standard deviations? Yes.
I don't know, we can be pretty confident that the mean is positive, right?
We can be absolutely certain that the mean is positive. You cannot increase the height of a tree holding the width constant and decrease the volume. So in fact, we could have declared these with a lower bound of 0. If we had wanted. In many situations, you might be highly confident that a regression coefficient is possible, but it doesn't violate any laws of physics for it to be negative, such as like the relationship between education and income or something like that. It could be negative for like some levels of education, even though we're pretty sure it's mostly positive overall. But in this case, inconceivable that the coefficients could be negative. We could still use a normal prior, but in this case, because we've declared beta to have a lower bound of 0, this would be a truncated normal prior. However, if the mean and standard deviation of this normal distribution are fixed, the amount of area being truncated away is a constant, and thus accounting for that would not affect the posterior kernel in log units. So returning to the question, we're pretty sure that the mean of both of these is going to be positive. So we could specify that as something like mu 0 and sigma 0, in which case, or, mu beta, sigma beta, in which case, what will we need to do?
Add those parameters.
Could be added as parameters if we wanted to estimate a hierarchical model. However, in that case, we'd have to take into account the truncation explicitly. In this case, we want to estimate a flat model. So mu beta and sigma beta would not be declared in parameters, but rather declared in data. It's a little bit unorthodox to consider, or it's not unorthodox, but it sounds discordant to think of these as data. But you can think of data as anything to the right-hand side of the vertical bar in Bayes' rule on the left-hand side. So we have a, let's say, real what do I call it? Mu beta. And I could pass in whatever.
And I think that should be sigma beta.
Oh, sigma beta. Thank you.
Is it excessive to put the lower bound on mu beta as well?
In this particular context, it would be reasonable to say mu beta has to be positive as well. In order to make this work for a wider variety of things than just trees, I'm going to take away the lower bound on that. In which case, we can just think of this as y and x and beta. And in another context, you could have a different mu beta and mu sigma. So the way I have written it here, which is the good way to write it, you can just pass in whatever you want from mu beta and sigma beta. In this case, you should be passing in two positive numbers for beta and pretty low or mu beta and pretty low values for sigma beta, because you could work out pretty much exactly what these coefficients would be, assuming a tree is a cylinder, which it's not exactly, but pretty close. So the only thing that can go wrong here, the only source of error is the lack of cylindricalness of a tree. Okay, and then we're also going to need what? Prior on the alpha. What would that be? Normal. Very popular distribution. And what are the prior hyperparameters for your prior on alpha? Mu alpha, sigma alpha. And where would we need to declare mu alpha and sigma alpha?
Data.
What?
Data.
Data. Correct. And in this case, they are scalars rather than real arrays. So in the context of trees, what would you think is a reasonable value for mu alpha? Zero? Really?
6 inches.
Hmm?
It starts at 6 inches.
No, because the outcome is in volume, not inches. So how in general do we interpret the intercept of a model? Right. It's the expectation of the outcome given that all the x's are 0. And if all the x's are 0 but they've been transformed to logs, what does that mean? So this is in log units, but what volume would you expect for a tree of 1 unit of width and 1 unit of height? Very small tree. Unless the units are in like I don't even know what units would make sense for those to be 1. But if they were 1, then what would the volume of that tree be? So volume is area of the base times the height. Area of the base is pi r squared. R is 1. Height is 1. So the volume would be pi. In log units, the log volume would be the volume is pi. The log volume is log of pi. That is what you should put from mu alpha. Don't know what that number is off the top of my head. You can calculate. Again, sigma alpha should be pretty small here because the only thing that could, go wrong is your tree with 1 radius and 1 height not being exactly a cylinder. Okay. Got prior on alpha, got prior on beta, we got log likelihood. What's left?
Prior on sigma.
Prior on sigma. What should we do for that? The standard deviation of the errors coming from tree not being exactly a cylinder. Here, you do have to consider what is the units of the outcome variable. Actually, you needed to consider that for beta and alpha as well, but particularly for the standard deviation of the errors. So if we measure radius and height in like millimeters, then the volume in millimeters cubed of a tree is going to be some huge number. And consequently, the errors are going to be, huge in absolute terms, even if they're sort of small relative to like the r squared or whatever. However, if we're measuring radius and height in like meters, then the volume in cubic meters is going to be a lot smaller. Standard deviation of the errors is going to be smaller. So this is going to depend on the units. And in general, it is useful in STAN to choose the units, particularly of the outcome variable, in order to make standard deviations be about 1, on the order of 1. So you can choose whatever units you want that will tend to make that happen. So if we wanted to specify a prior for a non-negative number that has an expectation of 1, what would be a good prior for that? Uniform between what, 0 and 2?
Should be the units, right? The units you expect maximum.
So I think what you're saying is you could have sigma be uniform between 0 and the height of the largest tree. But prior to seeing the data, you don't know what the height of the largest tree is. Might have a guess, in which case you could plug that in. But using uniform priors tends not to be that optimal in STAN. It's usually better to have a prior that has some non-constant shape to it. One of the things that we talked about now several weeks ago is that the least informative prior for a non-negative random variable with a given mean is exponential with rate parameter equal to the reciprocal of the mean. So presuming we've chosen our units to be such that we want the standard deviation of the errors to have a prior mean of 1, what exponential prior would we specify on sigma? Also 1. So we could do something like this. Exponential LPDF sigma 1. All right. Now we can click on the check button and it will tell us that we are syntactically correct but do not have a blank line at the end. That sometimes suggests you wanted to write more, but you forgot. So it gives you that warning message. But after outing the blank line, the warning goes away, and it tells us our STAN program is syntactically correct. That doesn't mean you can't mess it up in other ways, but it has valid STAN syntax and no invalid STAN syntax. So now we could call this thing, but we would need to add what? So the data we are slated to pass to STAN is only y, x, n, and k, and yet the data block of our STAN program includes all of those plus additionally what symbols?
The hyperparameters for alpha beta.
Yes. Mu alpha, sigma alpha, mu beta, sigma beta. We could also put in like a rate parameter of that exponential distribution if we wanted it to be something other than 1. So we would need to add to that like mu alpha log pi. And then, you know, that mu beta, whatever we work out for the coefficients. We'd have to do those for all of those. Otherwise, you will get an error message saying like mu sigma not found because you didn't pass it. Questions?
So the way you've written the model, still like the model part.
The model parts.
Yeah. So there's another way to write it, which is like more sort of like parts in the book, which is like saying y is normal.
Yes. So equivalently, you can write y is normal, mean function like this. Right. Yes.
You can do that for the beta and alpha.
Yes, that is equivalent. However, that is considered less instructive about what STAN is doing. It's not merely the case that you're saying like y is normal. You're defining a posterior kernel in log units. So it's considered to be more explicit to use the normal underscore LPDF, even though these two things translate to essentially the same C++ code up to a constant. You know, it's when you're learning how to write STAN programs, thinking about writing posterior kernels, we've, at least I, but not just me, other people as well, not everyone, but a lot of people, think that this notation is more explicit as to what is going on. You're adding the log of the normal PDF to this target thing, and target builds up the value of the numerator of Bayes rule in log units. It's also, more explicit what the random variable is, what you're conditioning on. But yeah, McElreath, his book, Rasmus, etc. They tend to use this other notation, which I will eliminate. Other questions? Yes.
What are some other potentially better choices we could have made for the outline beta parameters instead of normal distribution?
Normal is, not bad. Sometimes you will, or oftentimes you will see people use something that is heavier tailed than a normal distribution, like a T distribution, because they want to allow a slight probability that this coefficient is just giant. So at the extreme, you could use a Cauchy. You could do a hierarchical model and estimate the degrees of freedom of a T distribution, etc. Normal tends to be pretty good. Pretty easy, relatively easy to specify. Other questions? Yes.
Do you need to include the alpha, sigma alpha in the data frame?
Not in a data frame because those are just scalars. So I added a scalar here. So this DAT is just a list. It's not a data frame because the objects don't have to be all the same length. We've got some scalars, we got a matrix, we got a real array. So it's really just a basket of stuff as best as can. Other questions? Yes.
So in this case, your beta will be a list of 2 elements.
In R, it could be a numeric vector. That'll get, so if you give R, if you give Stan a numeric vector and you declare it as a real array, it'll just translate that. It's the same amount of storage either way. So yes, you could do, I'm not going to figure out exactly what these coefficients should be, but let's just say, other questions? Okay. So supposing we wanted to write a probit model. In this case, there's a data set in the RStanArm package, which can estimate probit models. So let's say we wanted to do this one by itself on wells in Bangladesh, I think. In particular, wells, most of which were contaminated with arsenic. And then there was some effort to try to get people to switch from drawing water from arsenic contaminated wells to less contaminated wells. So the outcome variable is, did the person switch their preferred well after being told like how much arsenic it contains? And that could be a function of how much arsenic it contains, how far you have to walk to haul the water back and forth, how educated you are, other stuff like that. So supposing we wanted to specify a probit model for this do you switch business, we could create a list of stuff from the wells data frame. Y is the outcome variable. X is binding these two things together. Here I'm taking the liberty of choosing the units on the distance variable to be like hundreds of meters probably instead of meters. So each one additional meter is probably not going to affect the probability that someone switches wells all that much. But if you had to go like 100 meters farther, then you might sort of think about how worth it is to you to drink water that isn't contaminated with arsenic. Even still, 100 meters is probably not that big a burden relative to poisoning yourself, but we'll put it in hundreds of meters. As usual, we'll have N and K, etc. So if we wanted to write a probit model, yeah. In the Stan language, how would we go about doing so? I'll give you a hint. It's pretty much exactly the same as linear regression with a different likelihood. Wrap the likelihood in the probit function. It's really more wrap the probit function into the likelihood, but I like where you're going. So we're going to need data. We're going to need parameters. We're going to need a model block, and we're going to need a statement of the likelihood, which you were saying was.
So we do, I think, the linear regression like last time, but at the end, there's a link function.
There's a link function. That link function is the probit, standard normal CDF transformation. Okay. So in the case where we have, what's the nature of this outcome variable? It's a what? Binary? Zeros and ones. Do you switch after being told how much arsenic is in your current well? So what is the likelihood function for binary outcomes? Bernoulli. And since we're talking about a discrete outcome here, it's the Bernoulli PMF. And the Bernoulli PMF takes a single parameter. And what is that parameter? Yeah, in this case, we're thinking about the probit model having integrated out the latent variable. So the utility, the what? Y. So yes, it's actually going to take two arguments separated by a vertical bar. Okay. So what in the Bernoulli likelihood do we condition on? Probability of a success. And what is the function that tells us the probability of successfully getting someone to switch their well under a probit model? X times beta. There's going to be an intercept in there. But alpha plus X times beta is, in principle, any real number. What we need here is a probability. How do we transform a linear predictor eta into a probability under a probit inverse link function? Total number of what?
We just put probit
You're saying like this?
When we probe it up here.
Ah. Well, there's no such function, but that was a good thought. This is a little bit subtle, but when you hit on a correct function in the Stan language, it makes it light gray as opposed to black. We could have looked up the functions involving Bernoulli. There is Bernoulli logic. There is no Bernoulli probit. But we could do this on our own. What is the inverse link function of a probit model? Mapping a real number eta to the 0 to 1 interval. Conceptually. What kind of a function takes a real number, outputs a number between 0 and 1?
CDF.
CDF. And the CDF in question here is
Standard normal.
standard normal. So what is the name of the standard normal CDF function in the Stan language? What is the name of the standard normal CDF in the R language? Well, that would be maybe the logarithm of the CDF, but the logarithm of the CDF would be a negative number.
Just the CDF.
Normal underscore CDF, that's a general normal distribution. And if we want to specialize that to a standard normal CDF, what would we have to call it with? What makes a normal distribution standard? 0 and 1. However, since we know or should know the name of the CDF of the normal distribution in the R language, we could see what that thing is called in the Stan language. So what is the name of the normal CDF in the R language? No. What letter do all CDFs in the R language start with? P norm or P. In which case, it will tell you all the functions pertaining to P norm in the Stan language. The so-called error function and the complementary error function, those are related. The normal CDF, which looks auspicious if we call it with 1 and 0. There's the LCDF, the logger of that, which we don't want. The LCCDF, which is 1 minus the CDF in log units, which we also don't want. There's phi approx and phi. If we looked on page 408, it would tell us a specialization of the standard normal CDF is called phi, capital Phi, which is a common representation letter, Greek letter, for the standard normal CDF. We see that the arguments to the phi function are either a scalar or a vector or a real array, and it outputs something of the same length. So what you were looking for when you said like wrap it in something is that. Take alpha plus x times beta, plug it into the standard normal CDF, get back numbers between 0 and 1, conditional on such numbers. That's the probability of the data before you observe it. After you observe the data, it's the likelihood of alpha and beta. All right. So in order to evaluate that likelihood function, what are we going to need in the data block of our STAN program? Which is almost exactly the data block of the linear regression that we wrote before. In the interest of time, let's just copy that and change it as needed, which is not very much. So what changes do we need to make to the data block of the STAN program to be appropriate for this probit model?
And parameters for feet.
There are no parameters for feet. It's standard normal. Could, and moreover, y is in this case a integer. All right. NK and x are actually declared the same way, even though x is no longer log height and log width of anything. Different variables in x, same structure. Okay. The rest of this is the same. What do we need to declare in the parameters block? And the nature of those are real for alpha. And vector, and when declaring a vector, we need to say k. What about sigma? Where is sigma?
One.
Constrained to be 1 in a probit model, which is why we're using the standard normal CDF. We could use any normal CDF with fixed standard deviation, and we get the same probabilities, but the standard deviation is not estimatable from the data, so we just fix it to some convenient number, such as 1. So in that case, sigma is not declared in the parameters block of a STAN program. It's not an unknown that we want to draw from the posterior distribution of. Okay, so what do we need in the rest of the model block? Priors, which are, or at least they could be, same as what we did before, or something different. So at this point, we have a syntactically correct STAN program for a binary probit model. Questions? All right. So, writing a STAN program for a linear regression model or a binary probit model while instructive, it's perhaps not the best use of time because you could estimate a linear regression model and or a binary probit model using functions that are available in RStanArm or VRMS. Once in RStanArm are already written and compiled, VRMS, it'll generate the Stan code on the fly, compile it for you, draw from the posterior distribution, etc. Where improving or dramatically improving your ability to write programs in the Stan language comes in especially helpful is when you want to draw from a posterior distribution that is not among the ones supported by RStanArm, VRMS, or any of the other like 20 R packages on CRAN that use Stan in some way, shape, or form. One of which to the best of my knowledge is not available in any of those packages, is the so-called conditional logit model, even though there's no such thing as a unconditional logit model. But this is, well, conditional logit is sort of an economics word. This same model is often used by public health epidemiology type people in so-called case control studies, which are a more efficient way of studying things like a rare disease. Because if you took a random sample of the people in the population, most likely you would not get anyone in your sample who has that rare disease. That could be a problem for trying to, predict or, figure out if your drug cures the rare disease, stuff like that. So what these epidemiological public health people tend to do is round up all the people they can find with the rare disease, pay them to be in the study. But at this point, you have a difficulty in that the only people you have in the study are y=1 people. Also not good for estimating the coefficients of anything. So what then they do is go out into the population and select K people who do not have the disease, pay them. Now they're in the study. So now you have a data set where you have variation on the outcome that you've obtained in a relatively cheap way. However, and in doing so, it's most efficient if you select K people that don't have the disease that are otherwise similar to one person who does have the disease in terms of their age and gender and stuff like that. So the one person with the disease and the K people who do not have the disease but are otherwise similar form a stratum. And within each stratum, by construction of this research design, the observations are not conditionally independent of each other because there's exactly one person in each stratum that has the disease, and the other K-1 people in that stratum do not have the disease. So you've selected your sample on the basis of the outcome variable, which is typically not advised by traditional statistics books, but in this case is the only cost-effective way of studying a costly disease. And if you do it right, you can still make inferences about the population if you know the prevalence of the disease in the population. We'll talk about that more later at the earliest. Anyway, these observations are not conditionally independent of each other. Maybe a simpler way of thinking about it is, what if you were modeling like the Indianapolis 500? It starts with like 30 cars, exactly one of which is going to win the race. The rest of them are going to not win the race. So if you want to model, who's going to win the next Indianapolis 500, you could use a conditional logit model such as this. The log likelihood of the data is not over the individual cars or whatever, but is the sum of the log likelihoods for each stratum. In this case, the log likelihood for stratum J can be written as the linear predictor for the person who wins minus the logarithm of the sum of the anti-log of the linear predictors for everyone in that string. So this is a pretty common construction in Stan, or in statistics really. The logarithm of a sum of exponentials. And Stan has a special function called log underscore sum underscore x that can evaluate that in a numerically stable way. So if we were going to write this in Stan, we might use it in a data set like this, where the outcome is case. I forget exactly what that pertains to. It has something to do with women. Anyway, I don't know. So there's a bunch of variables. We need to calculate capital J, which is the number of strata, obs, which is the number of observations in each strata. This is one of these case control deals. And we still have a coefficient matrix or predictor matrix X that has, various predictors. So we're basically saying conditional on exactly one person in each stratum having y equal 1 and the rest having y equal 0. What's the probability that each observation is the y equals 1 in that stratum? So we have n and k, and we need to write this model, and we need to write it quickly. So I will do that. We got a data block. We got a parameters block. We've got we don't have an intercept. So this model only has coefficients. There's no intercept. There's no sigma, anything like that. We're going to have n and k and x. And we're going to have j of strata.
I think that typo in the declaration thing, that should be enclosed.
Thank you. Stan will point out these errors for you, but it's always good to have a Stan developer who can also point out these errors for you. And we're going to have this indicator variable. We'll call obs, which is an integer array of length j, telling me for each of these strata how many people are in it. I think that's more or less all we need here. So we are going to construct a linear predictor that is a vector of length n called eta, which is simply x times beta. And then we are going to do a loop over the groups. So we have target plus equal. And what I said previously was the likelihood can be written like this. So we're also going to have, what do I call it? Successes. I don't know if these are actually successes, but int or equal 1 success is so first we're going to add the successes to the log likelihood. So that is going to be eta successes. And then we're going to go through and add for everyone else. So we can do something like this. So that, and this is a negative sign. The segment function extracts consecutive elements of a vector, starting at its second argument, which I'm going to call pause for position, and going in underscore j elements down that vector. So I just increment target by the negative of the log sum x of that, which comes from the slide. And then I'm going to increase pause by nj, so it moves to the start of the next string. And then, so that's log likelihood. And then we have prior on beta. All right, so this is hopefully mostly syntactically correct, except for the incomplete final line. All right. Usually it will take more than one take to get a STAN program correct. That's normal. But as you get more practice, you can write these things even when you only have like 3 minutes left in class when you start. Okay, so I'll upload these to Courseworks, but got to keep practicing writing stuff in the STAN programs. Do the exercise from the syllabus on writing STAN programs if you haven't already done so, and then hopefully a lot of this will kind of become second nature because a lot of the parts to it, particularly in the data block, are more or less the same parameters. There could be like a little bit of changing depending on if you do a hierarchical model, whatever. But it's pretty much just what's the likelihood, what's the priors, put that in the model block, and then do whatever you need to do to get to that point in the data, transform data, parameters, transform parameters blocks. All right, so I'll see you Thursday.
There's a comment you made that I missed, that we were doing those toy examples.